Thank you for the warm welcome and giving me this opportunity to speak in this forum. Briefing about our IBC technology, ZEBRAplus, based on the PolyZebra development platform. And I'll brief around the building blocks towards an industrial bifacial back contact technology. A short outline, a couple of slides about IC constants. We have heard today from our co-founder, Dr. Radhavan. Why BC technology? I think I also don't need to emphasize much more on that, looking in morning discussions. Then diving into the ZEBRAplus back contact technology, the building blocks going into the individual cell-related layers, and copper back contact, copper being a key topic or silver consumption being a key topic, and some conclusions and outlook. So about IC Constants, so we are a non-profit research organization founded in 2005, been 20 years in existence, and yeah, as Rado mentioned, Zurich is the nearest airport, so you're all welcome to visit our institute. We have a pilot line, development pilot line, using industrial feasible equipments for developing the technologies. We are 70 people, close to around 17 employees in total. And one of the achievements with the numerous technology developments, ramp-up supports, we have around 7 gigawatt support and technology transferred into mass production industry. And proud also to say these recent transfers have resulted around 25.3 efficiency running in mass production. That's related to a TOPCon production line. Our main activities, we are focused from the development from solar cells, technology development from cells, putting into modules and going into the applications in terms of systems, smart grid and agri-PV, covering also storage, including hydrogen. And towards all the value chain of our activities, education, training, and development cooperation forms a core pillar covering these main topics. A short track record of our transfers and ramp-up support. We have been 20 years of experience in development and industrialization of N-type cell concepts. So that's quite in the early stages, with the first ones bringing the NPERT technology to India, or the early ones to also in 2019-20, successfully also transferring the industrial lean process IBC technology in SPIC China, and also ramping up the first TOPCon line in India. So around 7 gigawatts from early megawatt scale to gigawatt scale of ramp up and technology transfers. So why back contacts? I think there's not much more to say. It's the last evolutionary field proven crystalline cell technology with proven processes and industrial equipment, and with the module efficiencies greater than 24%. Today we have seen ICO modules around 25%. So that's from the Taiyang News, the top module efficient manufacturers are from back contact. Looking in all the projections from different market analysts, there has been always a mixed response with low to high, but there is a common consensus that around 40% will be the back contact share in the next technology evolution. So I'll dive into a few more technical about our ISC ZEBRAplus based on the PolyZebra development platform, which has been presented in many of our discussions and presentations. The building blocks, let's go a bit more a step back, like what is Zebra? So this was a lean, industrial, low-cost, high-efficiency N-type technology. Been 10 years of development in 2009, based on PERC-like process equipments with diffused N plus and P plus typing. This is close to around being the diffused surfaces. And early, we were the ones who could contact a P-diffused region with silver metallization, with bus on flexible positions, soldering and bifacial, and transferred successfully in 2019 into mass production to one of our industry partners, SPSC. That's about Zebra with 24%, 700 millivolts of VOC. Looking ahead, so that's Zebra at SPSC, where these were the times when in 2020 the PERC was the mainstream and we had an efficiency of 22.8, but SPSC with the 200 megawatt IBC cell and module line, 24% IBC Zebra. But what it has also led, it's been quite amazing, and we are proud to also mention, with cooperating with partners, laser structuring, fast lasers for ablation patterning by DR Laser Tech, a three-dimensional screen printing, a cost-effective implementation of metallization, which brings in interconnections using classical stringing bifacial modules. So these were some of the key takeaways into the, which has triggered fast back contact development activities for industrialization in China. Moving to the next technology, that is ZEBRAplus, based on the PolyZebra development platform. This has been using TOPCon-like process equipment. We present a PCVD route back contact process route, a lean, high efficient, low cost back contact technology, where the key elements are the passivating contacts, polysilicon oxide P plus and N plus region, a laser-induced mask ablation and dopant activation, and a textured gap separating the two polarities, which also results into no need of single-side etching, and further screen printing of silver and copper metallization. Some of the key features of the ZEBRAplus back contact technology. So what is it has been a process in combination of industrial major process steps for TOPCon, from TOPCon, Zebra, and back contact, what ICO and others have been using. So one of the, I outline a sketch of the process. So it's a PCVD-based first process of the N-poly with some masking, then later with the P-poly with the PCVD boron diffusions, and continuing with the classical steps of either a TOPCon with wet chemistry, passivations, and screen printing. I'll dive into individual layers in the next slides. What is also supporting these developments are our strong IP behind it, starting from Zebra and PolyZebra, high throughput, efficient boron diffusions, then the complete PolyZebra technology route, and also the interconnections of the back contact. So this has been quite the backing our technology development with the IP. Moving to individual building blocks, we say it's TOPCon-like process with a PCVD route. So everyone is quite well aware of the TOPCon process. So one of the process is the N-poly and the annealing. That's quite well defined in the industry, a well-known process. So this is one of the building block for our N-poly layers. How about P-poly layer? Introducing very cost-effective, simple steps with a chemistry and a PCVD intrinsic oxide with diffusion, supported by laser. We can develop the P-polysilicon layers. How do we do this? Some of our know-how in the development of these layers. So with an accurate know-how of the laser energy density, one can really define the activation of the diffused boron layers. So in this example, with the laser density more than 1 joules per centimeter square, you see the laser activation of the boron layers being activated with a proper choice of laser power. So from let's say above 1, we can see the behavior, and then from 2.3 to 4 joules, one can really go into this super solid solubility limit of boron, and then have the defined properties of a passivating P plus poly layer. If the laser power is chosen above the process window, one can see the disruption of the tunnel oxides, the blue curve here. Yeah, the laser, yeah, here. So with the proper choice of the laser parameters, one can define the passivating quality of the P plus poly layer. So this we have integrated not only in back contact, but also in our early development of a both-sided contact, passivating contact popcorn layer, where we successfully demonstrated the passivation quality and low metallization losses from this, introducing the P plus poly layer, and this has also been validated. So with this, one can define a PCVD root poly, P plus poly, with a low J0 met and a good passivation quality. So let's integrate this into a ZEBRAplus IPC. So we know how we define the N plus poly layer, the P plus poly layer. The gap is the textured passivation gap. So how do we integrate? So I refer to our earlier notes from 2024, where 24% efficient solar cells were presented. And one of the challenges were to go beyond or close to 25 is to work on improved gap passivation and improved P plus poly passivation. So we've been working on that, finding optimum thermal budgets. So finding optimum thermal budgets during the integration process. So one of the process control, what we have introduced in our development pilot line is have defined structures for each layers, critical layers, the N poly layer, gap, and the P poly, and which has seen the complete process routes, and one can quantify at the end of the process what are the individual passivation quality for these layers, which has seen the thermal budgets of the complete process stack. So with this process control, which we can also introduce in mass production, one can easily quantify the quality of your front-end process. So I quickly browse about the P-poly justification, where defining a proper tunnel oxide and an annealing temperature supported by different group of experiments, we can target around 725, 730 millivolts of P-poly passivation quality. Performing similar optimization routes, we have obtained for the different critical regions after complete processing, around 738 for the N poly, a gap of 730, 728 to 735, and a P poly around 728 to 732 millivolts on test structures. And once we also integrate into a complete precursor, the regions specified are in the range of 729 to 732 millivolts at the precursor level. With this, diving into how about metallization. So we have also defined in-house to screen different metallization fraction, metallization paste, and co-firing to quantify the J0 met and contact resistance. These are our test structures and our test screen. With this optimization experiment, one has to find suitable co-firing parameters with a very low, which can contact both the P poly and the N poly, providing low J0 met and low contact resistance. So that's one of our parameter benchmark, having less than 2 or less than 1.5 milliohm centimeter square for both the contact resistance, both the poly layer contacting. What we have also presented in the recent publications as well, with a proper choice of this know-how and the paste, one can see IVOC to VOC loss of greater than 8 millivolts, and with a paste P choice, one can restrict a passivating contact behavior with a less than 2 millivolts from precursor to voltage final cell VOC. With this know-how, I mean, the latest development, which is in this month, which were yet to be printed, so precursors are waiting printed, but we are quite confident that the efficiency expectations, the VOCs would be 725 millivolts with the know-how of the metallizations and the passivation qualities. And we are expecting 25+% efficient cells in the coming weeks. With this, on the ZEBRAplus, we also look into screen-printed copper. Screen-printed copper, we have been working quite in the early stages in the Zebra development, and also transferring those know-how into the polyzebra with a seed layer of silver and copper metallization on both the polarities. So in the recent developments demonstration, silver consumptions less than 4 milligram, 4.5 milligram per watt peak, and the cost of ownership reduction goes to $0.8 cents with compared with the standard TOPCon. Also on plating, we have been working with our industry partner PV2+, integrating also plated metallization on polyzebra. So know-how from PV2+, the PVD metal seed layer with copper barrier diffusions, excellent adhesions, and low contact resistance electroplating, with aluminum masking of non-expensive organic resist and high cost saving potentials towards 100% grid silver-free. So with this, I come to my conclusion and outlook. So presented a PCVD route ZEBRAplus back contact built on TOPCon-like process equipments with a strong family of patent. A pilot line, ISC pilot line efficiencies at 25+, and a copper metallization towards high efficiency and low cost. An outlook, Zebra in mass production, 26% cell and 24+ in module efficiency, where my colleague tomorrow will outline few of our module developments at ISC. And thank you, and I acknowledge all our industry and research partners, project funding, and all my ISC colleagues, last but not the least, supporting the back contact development. Thank you.